This video is possible thanks to contributions to the Existence University Patreon by viewers like you. Thank you. Quantum physics is the study of matter and energy at the most fundamental level. Things get a bit weird by 1923, as this new field had people more closely examining what an electron is, what properties it has, what an atom is, if protons and neutrons are as fundamental as they get. Can we split an atom? One weird result comes from Einstein, who says that light has no mass, but it has momentum, which we can think of as mass times velocity. And that light might curve around massive bodies, because it has momentum rather than mass. Another weird result comes from Louis de Broglie, who takes the fact that electrons and photons are related, and that the photon has momentum, and finds that the electrons in motion have a reverse type of manner, such that it has a wave function. A year earlier, Otto Stern and Walter Gerlach discovered that electrons appear to have spin, and no one knows what that means. It appears to be related to angular momentum, but it has a half spin, and it wouldn't make sense to literally say it half spins like a top. Wolfgang Pauli showed that because of this spin property, objects with identical states cannot occupy the same space. And this actually explains how the periodic table of elements works. At the same time, Satendra Nath Bose says the opposite about photons, or bosons, as they get named after him, where bosons can share the same state and space. The introduction to the modern approach of quantum was given to us by Werner Heisenberg. Heisenberg himself stated that he was determined to base his quantum mechanics exclusively upon relationships between quantities that in principle are observable. Sticking to the more simple case, he thought about the radiation of an excited hydrogen atom, rather than the radiation from the boiling, bubbling, mysterious sun. In quite the same way as Maxwell and Boltzmann, and Stefan and Raylan and Jean, Heisenberg was looking for intensity, or energy values from the radiation. But he needed only an electron moving from a high energy state to a low energy state, thus releasing a photon of measurable energy, or wavelength, or frequency, or momentum. Heisenberg discovered something weird about atoms in doing so, as he found that the law of multiplication, which would be needed to describe certain properties of the atom, did not work both ways. For example, if he took A first, then timesed it by B, that would get a different result from when you started with B and timesed A to it. This is called non-commutative multiplication, and it is very strange on the classical level, and yet seemingly fundamental on the quantum level. One of the best ways to deal with quantum, therefore, involves using complex numbers, which introduce what are called imaginary numbers to all of the real numbers we know about. This led to the fighting about what it means to be, quote-unquote, real. In 1927, Heisenberg provides us with a fundamental concept of quantum mechanics, the uncertainty principle, which states that there is a limit to the precision with which certain pairs of physical properties can simultaneously be known. Such examples are position versus momentum, or energy versus time. The formulation comes from subtracting that non-commutative multiplication law, which results in the equation P times Q minus Q times P equals H over 2 pi I, which is converted into the famous equation sigma x sigma p is greater than or equal to h bar over 2. This suggests that differences in the multiplication between p times q and q times p cannot be measured at the same time. There is always this little extra bit of stuff that says they are not quite touching. Imagine p and q are sides of a square. The math is saying p length times q width, p times q, area, and q length times p width equals QP area. In our classical world, these areas are the same, so PQ minus QP has to equal 0. This means that we can measure them at the same time by putting one on top of the other. When PQ minus QP does not equal 0, this means that if we place PQ on top of QP and see how much area is left over, somehow there is a tiny amount left, such that we can never be certain if PQ is the same exact place as QP. Finally, to complete this video, we return to the start. The rock creature we formed. From our thought experiment, we realized that energy comes in a certain geometry. And as we moved into the history, we talked about how we, as cavemen, thought the earth and sky were flat. Or that the earth was flat, and the sky was a surface, the inside surface of a sphere. Then we realized that we are on a surface of a sphere. We formed a three-dimensional Euclidean model of space based on what our eyes see. So follow along with me on this other thought experiment. Close your eyes for a moment. When we open our eyes, a spherical world emerges. The world of light exists on the surface of a sphere, emitted from the surface of a sphere, received by the surface of a sphere. If we were one-dimensional beings, our experience of the world would be one-dimensional. But two-dimensional and three-dimensional beings know about circles, which they describe to us, as one-dimensional beings, as a world where all of the circle below us, whatever that means, is mapped in our line of space that we see and live in, and that all of the circle above us, again whatever that means, is mapped beyond our comprehension, and that at the very top of the circle is mapped such that it is infinitely far away in either direction. Somehow, it is all the way left and all the way right infinitely at the same time. Very strange. If we were two-dimensional beings, a three-dimensional being would tell us about spheres existing, and that one could map that sphere onto our plane of existence, such that everything above our plane is mapped into the circle of our world, with what they call the North Pole at the center. The parts of the sphere below our plane are stretched out infinitely in all directions, such that all directions away from the North Pole head towards the South Pole, which is infinitely far away. So to the one-dimensional being, circles seem impossible, and go off in both directions infinitely. To a two-dimensional being, a sphere appears to be outside of a circle, stretching infinitely outward from that circle. Now wait just a moment here. We are three-dimensional beings, who believe by the nature of reality that the universe is finite in size, but we also appear to see a sphere which stretches out infinitely in all directions. Matter of fact, it would appear quite simple to extrapolate that the appearance of the universe being spherical and infinitely expansive, that it just might be the case that we cannot see the next dimension up. Given that when we lived on a line, we thought the universe was a line that stretched away infinitely in both directions. And we can easily explain that on a plane, as it would appear to us in the plane that the line being is walking infinitely because it is just walking in a circle. When we live on a two-dimensional plane, the universe appears like a flat, circular plane that stretches out infinitely. And we can explain to that plane being that when he walks in one direction infinitely and wraps around, that is actually because he's walking around a sphere in a higher dimension. A sphere just being a circle in all the ways at once. So what if we send a probe to the edge of the universe, we are just sending a probe around a four-dimensional hypersphere, which is just a way of being all the spheres in all of the ways at once. Now that doesn't make sense to your brain, but it also wouldn't make sense to some living cartoon that you draw on a piece of paper when you tell him that you're going to flip him over. This is symmetry, and in 1918, Emmy Noether provides us one of, if not, the greatest and most important theorems of all time. For every continuous symmetry of action of a physical system with conservative forces, there exists a corresponding conservation law. Throughout this history, we are collecting these laws. We found from Newton the conservation of momentum, and from Helmholtz the conservation of energy. According to the theorem, the conservation of momentum and the conservation of energy must have a corresponding symmetry of action, which is also stated alongside them. Momentum is conserved over space, and energy is conserved over time. When Einstein combined energy and mass, the conservation of mass law by the chemist Lavoisier was added to the conservation of energy law, both conserved over time, which we stated in this video when we said that Newton's second law of motion is momentum over time given force, and that was mass times velocity over time, as mass does not change over time. Noethers Theorem explains why then Newton's law works. The symmetry of linear momentum is the space translation invariance. All places in space follow the same laws of physics. That is the symmetry here. The symmetry of angular momentum is rotational invariance. Rotating a ball in any direction still makes it look like a ball. The mass-energy conservation is caused by the symmetry that time translation is invariant. The laws of physics are the same today as they will be tomorrow. The ability to change speeds in reality, or boost your 3-vector, is caused by the symmetry of Lorentz boost invariance, meaning special relativity is valid and there is no such thing as a universal speed. The conservation of electric charge is caused by a symmetry in scalar potential fields in phase space. The conservation of color charge in quarks is caused by the symmetry of chromodynamic potential fields in phase space. The conservation of weak isospin is caused by the symmetry of weak potential fields in phase space. The universe, therefore, is full of stuff, because it is full of symmetries. And things we see having symmetries are caused by the fact that energies and properties are objectively conserved. And given that we see symmetries all around us, the same one in fact, where it takes 360 degrees of rotation in any dimension to return to normal. And yet, the quarks and leptons that make up all of these 3D 360 degree spinning objects are themselves required to spin 720 degrees of rotation to return to normal. So are we merely experiencing the universe one dimension lower than we could be? Or many dimensions out of place? That question we leave for quantum field theory and attempts at quantum gravity. This was messy and long, but the history of quantum mechanics is. It has an infinite amount of path formulations into it, and this was just one. I hope you enjoyed the journey. This video is possible thanks to contributions to the Existence University Patreon by viewers like you. Thank you.